In this video, we will be looking at algebraic vectors in 3D. So all of the operations that you should already know regarding algebraic vectors, like writing the algebraic vector with components, with unit vectors, finding the magnitude, adding, subtracting algebraic vectors, or multiplying by a scalar, all of those rules are the exact same for algebraic vectors in 3D. The only difference is we have an extra dimension and the visual is different because it's now 3D instead of 2D. So let's start off by looking at the 3D nature of vectors. So first of all, in 2D, we're just considering the x and y axis. In 3D, we now have the z axis as well. So our z-axis is actually going to be the vertical axis. What used to be x is now y. And the x-axis is this axis that is kind of jumping out of the page at you. Now, the three x, y, and z axes that I drew, these are the positive sides. The negative side of the x-axis is behind the page. For the y-axis, it's to the left. And for the z-axis, it's below. So try to visualize this new grid as just the corner in a room. If you look at the corner in whatever room you're in right now, that vertical is the z-axis. The edge on the ground, one of the edges is your x-axis, the other is your y-axis. And with this visual in mind, we'll get into the position vector. A position vector always has the tail at the origin. So here we are, and its head at any point, and in 3D, that point is going to be point ABC. And we'll connect, let's say, a random point here, and there's the vector. And we can write that vector using square brackets and then ABC. Now, we know we can also write our vectors using a linear combination of unit vectors. So what are the unit vectors for x, y, and z? Well, our x component is still I, except now we have the vector as 1, 0, 0. And this is the vector that has a magnitude of 1. Its tail is at the origin and its head is at an x value of 1, but the y and z values are 0 because this point lies on the x-axis. Likewise, the vector that is along the y-axis is vector j, and its tail is at the origin, but the coordinate that it ends at is 0, 1, 0. So that is unit vector j. And finally, the one that is different is the unit vector that goes along the z-axis, magnitude of 1. The x and y components are 0, but the z component is 1. So we can write that position vector ABC as A times vector I plus B times vector J plus C times vector K. Now, going back to our grid in 3 dimensions, I want to mention the different planes that we have. So the plane formed by the x-axis and the y-axis, so this right here, imagine the ground. If you look at that corner in your room, it is the ground. That is the xy plane, and every single z coordinate on this plane is 0. And that's why the equation of this xy plane is just z equals 0. Next, we have the plane created by the x and z axis. So this plane here has its y coordinates always being equal to 0. So the equation of the xz plane is y equals 0. And that could just be one of the walls near that corner. And finally, the YZ plane is created by the Y and Z axis, And every x coordinate on this plane is equal to 0 because this point is not coming forward or going back along that x-axis. So now let's actually draw a vector in 3D. And I'll go over magnitude in a minute. So we're going to draw the point 2, -4, and -6. And I'm going to start with my z-axis, my y, and my x-axis. Now, when we draw a point in 3D, we're going to create a rectangular prism out of the coordinates that were given to us. So, my x-coordinate is 2. So I'm going to label 2 out front. I'm coming forward because my x-coordinate is positive. My y-coordinate is -4. So I'm going to extend the y-axis in the negative direction, so to the left. And now 1, 2, 3, here's -4. And finally, the z-coordinate is negative, so I'm going to extend the z-axis downwards. And here's -6. And now I'm going to create each surface of this rectangular prism. So I'll start along the x and the z-axis. Now this surface that I just drew is part of that xz plane because it is made up of the x and z axis, and that equation of that plane is y = 0. Now I'll do my top surface. This top surface is made up of the actual x and y axis. That's your xy plane. Next, I'll do the front surface. Now, this front surface is not made up of the y-axis and z-axis, so it's not the yz plane. That one is actually the surface behind, the one that I just drew. That's the yz plane. The one in front has a constant x value, but it's not x = 0. All of the points on this front surface, x is equal to 2. But it's parallel to the yz plane. And then finally, to finish my box, I'll just show this. Now, here's the origin, and the actual point is the furthest point from that origin. It is right here. If you look at this point, it is coming forward. Okay, so it's coming forward 2. So it's at the front of the rectangular prism. It's gone to the left -4, so it's to the left of the prism. And it's at the very bottom when z is -6. And if I were to connect my origin to this point, this is vector OP. Now I can write vector OP using components. So 2, -4, and -6. Or I can write it using unit vectors. So this vector here is made up of taking double vector I, quadruple vector j, but in the opposite direction. And if I were to add this with this, the I and the j components, the resultant is this diagonal here. And now if I take that and I add on 6 times vector k, but going in the opposite direction, our resultant is in fact vector OP. So it is just the sum of those unit vectors that are being multiplied by a certain scalar. Let's hop into that magnitude now. In 2D, the magnitude of an algebraic vector is just the square root of a squared plus b squared. In 3D, it's almost the same thing, we just have to add the plus c squared component. So here's a little proof for you. This is the goal. That's our vector OP. Now I can create a right triangle from that vector, made up of this diagonal, the diagonal of that base, and this vector here, which is the vertical. Now I already know what the length of the vertical is. It has to match that z component, which is c. So I know this length is C. Now this diagonal here is just the hypotenuse in the right triangle where this length is A and this length is B. So to find that magnitude, I'm just taking the square root of A squared plus B squared. So the magnitude of OP is this squared plus the C squared, and then all square rooted. So let's see what that looks like. The square root of A squared plus B squared, all squared, plus C squared, and that will be square rooted. And if we clean this up, this exponent of 2 cancels the square root, and then we're just left with the square root of A squared plus B squared plus C squared. And that's the magnitude of a vector in 3 dimensions. So let's try that for our vector. So for vector OP, the magnitude is the square root of 2 squared plus negative 4 squared plus negative 6 squared. And if we punch that into our calculator, we get the square root of 56. And 56 can be written as 4 times 14, which means the exact value is 2 root 14 units. Finally, let's label all of the intercepts on this rectangular prism. So here is my x-intercept. For this x-intercept, the x value is 2, and then y and z are both 0 because the only movement from the origin is coming forward 2. There's no right left for the y or up down for the z. This here is the y-intercept. There's no forward movement, so x is 0. Y is negative 4, and there's no up-down movement from that origin, so z is 0. Finally, the z-intercept, there's no movement forward or back, or right or left, so x and y are 0, and z is negative 6. Now I'm also just going to highlight those planes again. So here is the xz plane made up of the x and z axis, and then that plane can span forever in all of the directions. Then I have yx plane on the top surface, and finally the zy plane in the back. And of course we have other planes that are parallel to these ones, like the back surface is parallel to this front surface. The sides are parallel, and front, top and bottom are parallel. So we do have parallel planes here, but the ones I've highlighted are specifically the xy, xz, yz planes, where the equations are just one of the coordinates is equal to 0. But actually, while we're here, let's just look at each of those planes. So I'm going to start with the one I highlighted in yellow. This is the xz plane. All of the values here are y equals 0 because there's no right-left movement. For the red plane, there's no up-down movement, so z equals 0, which is great because this plane is made up of the x and y axis, so it's the xy plane. The blue plane in the back, there's no front or back movement, so this equation must be x equals 0, and that is in fact the yz plane. Now let's look at the other 3 planes here. The front surface. On this surface here, the front of the rectangular prism, there is movement in front, and all of the x coordinates on this plane are equal to 2. Now there's movement right, left, there's movement up, down, because this can expand up and down and to the right and left forever. But in terms of the x value, x is always equal to 2. Let's look at this side surface. This side surface is parallel to the xz plane. And if you look at this plane, all of the y coordinates are -4. And finally, on the base, we're at a consistent z, and all of the z coordinates are -6. And that plane is parallel to the xy plane. So just a little bit about planes within that three-dimensional space. Now let's move on to those operations. So these are all going to be the exact same as in 2D. If I have two algebraic vectors, these are in 3D because we have three components, x, y, and z. If I want to add the vectors or subtract the vectors, I will just add or subtract the corresponding components. If there's a scalar multiple in front, I will just multiply each of the components by that scalar. And finally, if I'm given 2 points, these are not vectors, these are points, and I want to find the vector from one point to the other, I am subtracting the appropriate coordinates. So if I want to go from P1 to P2, I'm going to subtract the coordinates from P1 from the coordinates of P2. And then I can calculate the magnitude of that new vector. So let's try a few examples. We're going to start off with the magnitude of vector OA. First of all, vector OA is just from the origin to point A. So this must be my vector. The magnitude is just going to be the square root of 3 squared plus 6 squared plus 1 squared. And that will simplify to the square root of 46. Next, let's find vector AB. So we're starting at point A and ending at point B. Because we want the correct direction, we're going to have to do the B coordinates minus the A coordinates. So -1 subtract 3 for the x component. 0 subtract 6 for the y. 5 subtract -1 for the z component. And now I'll clean up. So this is -4, -6, and +6. So there's one way using our components, but we can also use our unit vectors. So -4 times vector I, -6 times vector j, +6 times vector k. And now let's find the magnitude of vector AB. So I'm going to take the square root of these components that I just solved for. The square root of -4 squared plus -6 squared plus 6 squared. That gives me the square root of 88. And 88 can be written as 4 times 22. So 2 root 22 units. And back to collinear. Find a vector that is collinear to AB. So we just need to be parallel to vector AB. And the definition of collinear is that you can write one vector as a scalar multiple of the other. So I can pick any k value and multiply AB by it. For example, maybe I'll just multiply my vector by 2. So here is a collinear vector. Okay, one more example. I have vectors u, v, and w, and we're going to simplify each expression. So we're going to start with some scalar multiplication. So I'm going to take vector v and multiply it by -3. So I'm just distributing that -3 in. So I have -24, 12, and -9 as the new vector. Next, we want to do vector u plus vector v plus double vector w. So I'm going to clean up my multiplication, and while I do that, I'll also just add u and v. So that's 10 minus 1, and negative 2. Just adding the x, y, and z components. And then I'm going to add double vector u, so that's negative 12, negative 4, 0. And now we can do that final addition. 10 plus negative 12, negative 1 plus negative 4, and negative 2 plus 0. Finally, we want the magnitude of vector u minus v. I am going to start off by finding u minus v. So 2, 3, negative 5, minus 8, negative 4, 3. Careful with your signs here. 2 minus 8 is negative 6. 3 minus negative 4 is 7. Negative 5 minus 3 is negative 8. And now that I have my vector, and please note here, we're subtracting vectors, so we are just applying the operations in the order we are asked to do so. U and V were not coordinates. We weren't trying to find a vector from 2 points. So we're not doing V minus U as we would have done here. It was not that situation because U and V were actual vectors already. All right. Now magnitude, so the square root of negative 6 squared plus 7 squared plus negative 8 squared. And when you clean that up, you get the square root of 149 units. And that's it. So the operations are very similar to just regular simplifying algebraic expressions, but these are vectors. Just be careful with your signs and making sure that you solve for the correct thing. Are you solving for the vector or are you solving for the magnitude?